this right here? H2O, H2SO4. What is the product? Anybody?
Keto.
Ketone, okay. So this is a four carbon chain, right? 1, 2, 3, 4. So where do I put the ketone? Where do I put the carbon?
On the second one.
Here?
Yeah.
Okay. And I don't know if you remember, we had this a while ago there. We had H2SO4. What do we make? We just had this one. Like we looked at the mechanism of this thing. Ketone?
Yeah.
Okay. Where's the carbonyl? Like this, right?
Yeah.
Okay, that's my point. Okay, I'm gonna leave it there. Okay. Ah, exciting, exciting. Okay, so see how my point here was. You see how this triple bond has two methyl groups on each, has a methyl group on each side. We get the ketone. You see how this triple bond doesn't have a methyl group on this side. It's only hydrogen. Yet again, we make the ketone and the same one. That's my point. Right? The point is that you can make the same thing from something that looks slightly different. So it could be useful, could be useless, but that's the point. The point is you can make these two identical from these ones. Okay, what about this old reaction, which is, let's go here, which is BH3, CHF, and then what did we have? What's the second reagent here?
5%.
H2, yeah, peroxide, right? And then we probably have some base, sodium hydroxide, and maybe some water. Could be all in the same mixture. Okay, yeah, this thing. Remember that thing? Yes? Super. So basically, the mechanism is the same as a double bond. The pi bond attacks the proton on BH3, and the boron attacks at the same time. So everything. So BH attacks at the same time. So let's look at this mechanism. Then 21. So this is what I had, right? So first step, BH3. So typically we draw BH3. I'll just draw it like this, even though it's a dimer. What I'm saying is you're making these bonds and you're breaking this one, right? So the BH comes onto a triple bond and then. Okay, so we make maybe something like this. What am I missing here? What am I missing here? Double bond, right?
Bond.
So it was the same adding like you added to an alkene. You basically added BH to the same face of the triple bond or a double bond. They're all planar, basically. And then I do this 2 more times, right? Right? Because you have to have these 3 alkyl groups around. So I end up with something like this. And somebody asked me, can we put just R group on the exam instead of drawing them? You can, but you have to first show me, you first have to show me that you form it, and then later, so what I'm saying is, show me first this, and then you can replace this with like BR, and then one of them. You know what I'm saying? So you can later say BR. It's okay. Boron with R groups. Just in the beginning, show me at least how they look like. Then what happens? That was the first part, right? With the BH3 or BH3 adduct with BH. What happens then? You make an alkyl borane. Then what happens with alkyl borane? Yes. Takes off the boron. Peroxide comes in, and then you have 1-2 shift of carbon from boron to oxygen. So H2O2, then you have something like this. Basically, oxygen inserts into, so now this is my, I don't want to lose track of my double bond to triple bond. Hydrogen, something like this, right? This is still R and R, right? And I still have OH here. Yes? No? Maybe? No idea? Anybody remember this mechanism from alkene? Is there something wrong here? Should not lose this? Anybody? Okay, I'm gonna move on. I'm gonna move on because it's the same mechanism as before. O, B, O, R, O, R. Hydrogen, metal, metal. So that's my OR, and then what happens is we cleave this by OH minus attacking there. Make this a very good leaving group, but not at the same time. So properly OR, OR, O, metal, metal, OH minus, and then this is a nice leaving group. And so this is what we form. Double bond, hydrogen, this, OH. Right? This leaves and then gets protonated. What is this? Anybody? Eno 3 times. Eno. This is still Eno, right? This is an Eno.
So then we change it to the ketone?
Yes, yes. So then we do this tautomerization and we base is here, pick this up, make this double bond and pick up a proton from an acid. And then we make something like this. I don't want to lose anything. Let me know if I lost anything.
So we make that 3 times.
Yes, yes, we make that 3 times. So this is a ketone, right? Yes? You remember how alkene, like if it's stable with an alkene, and water addition under acidic condition gave you an alcohol, and then if this was an alkene, BH3, then oxidation gave you alcohol as well. Right? So with the double bond, with both reagents, you get an alcohol, and here with double bond or triple bond, both reagents can give you a ketone. Right? But what was different about alkene and these 2 reagents? Alkene and water, acidic water, and alkene and BH3. What was different back then?
You got an
Auntie? Which one? Did not rearrange, right?
No.
There's no carbocation. So that's another difference. So one difference is no carbocation formation in the BH3 mechanism. And then the other difference is if you have a chance for carbocation formation, you immediately form the most stable one, which gives you the Markovnikov product. But then with the BH3, the boron always likes to add onto a carbon that's less substituted. So you can have a anti-Markovnikov product with BH3 and double bond. I hope you're following, because if you're not, it's going to be tough on Monday. So what I'm saying is alkene with acidic water can give you alcohol, and it always gives you the most stable alcohol, because you form the most stable carbocation. But the BH3 and the double bond also can give you alcohol, but you form a, yes, which is counter-truly less stable one. But yes, you form anti-Markovnikov alcohol because you never make a carbocation, and hence there's no choice for you to, for that type of differentiation. So with BH3 you make a terminal alcohol, basically OH is at the end of your double bond, right? Could be. Okay, so what I'm saying is, I'm not going to go over it out here. You guys should know this. The BH3 addition on the double bond will only give you primary if it's a terminal double bond, right? If the double bond is in the middle of the molecule, you can never get a primary because, right? Okay. So my point here is a triple bond. I'm adding BH. Look what's on the 2 sides of these 2 sides of the triple bond. methyl and methyl. And surely after all this reaction, I end up having methyl on one side and another carbon on the other side. Because I was just adding a boron there, I replaced boron by oxygen, made an enol, and then enol collapsed into ketone, right? Okay, what about this one? I'll keep this. What about this one? Oh, this we can finish, so let's do our circle. What do I get here?
3 ketones.
Where is the carbon?
A second.
Okay, I'll put it here. So it's that thing, right?
Would I add some kind of carbon dioxide that was the terminal?
Ah, this is where I'm going to. So